All right, our next presentation this morning is on big data for our urban infrastructure. Our speaker is Stephen Koonin, who is the founding director of NYU's Center for Urban Science and Progress. And that's a consortium of academic, corporate, and government partners who are pursuing research and education activities to develop and demonstrate informatic technologies for urban problems in the living laboratory of New York City. I know we all are aware of the stress that just human life puts on infrastructure and how we have a lot of failing systems. And Stephen's going to just show how many areas can be integrated of data that's already out there and how it can be used. So please welcome him to the podium.
During my time in BP and the U.S. Department of Energy, I came to understand the importance and the challenges in constructing large, one-of-a-kind facilities, and so my admiration for what you all do. My subject today is cities, where a growing majority of the world's people live. So cities are important, but they're also complicated. Probably the most complicated entities that we humans construct. A city is a system of systems, the infrastructure, the environment, and the people. These all play together. All cities have to be better than they are. They need to be efficient, they need to be equitable, and they need to be sustainable. In order to improve cities, we need to understand them better. And fortunately, there has been a rise of data technologies in the last decade, improvements in the ways in which we acquire, integrate, and analyze data. Those technologies allow us to better understand and so improve cities. For a city, we have all kinds of data available to us. The data that the city generates as it goes about its business, permits, tax records, operational records. We have a proliferation of sensors, whether it's portal sensors, the sensors that exist in rooms to measure temperature and light, or the sensors that we all carry around in our pockets now. And then finally, there are opportunities to apply novel sensor technologies to cities. What I'd like to do in the remainder of my talk is to stretch your minds a little bit and show you the new ways we have of looking at cities. And then I'll make some remarks about applying big data technologies to complicated enterprises, not only cities, but the kind of activities that you all are involved with. Let me start with city records. This is an example of the kind of data federation that Mayor Bloomberg established in New York City during the last 4 years of his tenure as mayor. And you can see that there is a tremendous amount of data, tens of gigabytes a day, that the city generates in the course of its operations. We also have for cities U.S. Census data. This is a map of the New York City area showing the Gini index, which is a measure of income inequality. While the details are not relevant now, what is important is that you appreciate the resolution, the level of detail that we have data about the city available to us. Here's an example perhaps more directly relevant to the kinds of things you do. New York City collects information about the energy use of its large buildings. And what this shows is a histogram of the energy use intensities of 1,150 office buildings in New York City. You can see that some buildings use 3 or 4 times the energy that other buildings do per square foot. That's due to the way in which the building is constructed, the way in which it's operated, the kind of activities that go on in the building, or sometimes just plain old misreporting. When you look at a similar histogram for residential buildings or apartment buildings, in this case 7,500 of them, It's a bit more normally distributed, but you can still see that some buildings use 2.5 or 3 times the energy per square foot that other buildings do. We have the ability then to start to drill down into this data. What's shown here is the energy use intensity as a function of the year in which the building is built. And if you focus in on that light blue line, you can see that the old buildings are in fact more energy efficient than the new buildings, presumably having to do with the glass curtain walls that those new buildings have. Unusual records data. These days we have tweets. New Yorkers have 2.6 million accounts. There are hundreds of millions of tweets a year, and we have technologies now that can parse those tweets and fish out interesting information. For example, some students at my center recently developed an algorithm to find leads for consumer fraud that are contained in the tweets. For example, when somebody says, Barclays Bank still owes me $600 and it's 10 weeks since they last contacted me. Cell phones are a wonderful source of information. This is an illustration of some work that was done at MIT and Stanford, in which they analyzed the cell phone locations for 500,000 phones over 6 weeks. The large map here is in the Bay Area. You can see that the lower right-hand corner, the road East Hamilton Avenue in in San Jose is fed by 51 different cell tower areas during the morning commute. Daly City in the upper left is fed by only 12 cell tower areas. This is invaluable information for people who plan the roads and operate the roads, obtainable before only by taking a survey once every few years of a few thousand people. Taxis are another feature of urban life. In New York City, there are 13,000 yellow cabs. They make 500,000 trips a day. And for the last 6 or 7 years, we have data on every taxi ride that was executed. Where did they start? Where did they stop? When? Fare, time, tip, driver, etc. This shows an example. 1 week in May, 3.5 million trips. We've segregated out the trips that start in the train stations in green versus those that start at the airports in red. If you focus in on the upper right panel, you can see at 15-minute resolution, there is a regular recurring pattern every day of the week, presumably having to do with when trains or planes arrive. The upper right shows the number of trips. The lower right shows the tips per unit time, and you can see that there are more trips out of the train stations, but larger tips out of the airports. Analyzing this kind of pulse of the city that you see is very important to understanding how the city can operate efficiently, detecting precursors of events that might go on in the city. Sensors are something many organizations are exploring now in cities. At CUSP, we have developed a $100 box that is acoustically accurate to plus or minus 2 dB and can be used for noise detection, noise characterization, and noise enforcement. We've started to deploy these boxes around the city, and a very important feature of them is a machine listening algorithm which both circumvents the legal prohibition of recording sound on the street, but also does feature extraction on the sound to tell us what the sounds are about. I don't know if we can play that audio just by clicking on it. And so what you can see is that the machine listening algorithm is able to correctly characterize in real time the kinds of sounds that it's hearing. Okay, let's go on. Noise is the biggest source of complaints in New York City. I grew up in New York City, didn't live there for 40 years and came back. It's a wonderful place, but the noise is driving me crazy. And I swore I was going to get that guy who was banging the trash cans at 2 in the morning. So we're well on the way to doing that. Mobility of people is important in a city. There are networks, growing numbers of Wi-Fi access points in the city. They ping every Wi-Fi device that passes by it by analyzing, in this case, a network in Lower Manhattan. The pings: did I see that device before? When did I see it yesterday? Is it the first time I'm seeing it? You can segregate the population into residents, workers, and passers-by, and get a better sense of how people are moving around the city. This shows you about 2 weeks' worth of data in July. You can clearly see weekdays, weekends, the 4th of July holiday, etc. Yet a different way of looking at the city is to literally look at it. And that's illustrated by this image, which is taken in the thermal infrared. If we look carefully at that building, you can read the thermostat setting of every apartment in the building non-invasively. If you look at that building, we know it's got a data center in it, and so it's hot on the bottom and hot on the top where the vents are. And that set of buildings is public housing, where in characteristic New York fashion, they've got the heat turned up full blast, and people are cooling their apartments by opening the windows. When you think about it, this is a remarkable picture. It's a single sensor, a special sensor, infrared, but nevertheless a single one. It's giving us synoptic coverage. We're looking at several hundred buildings in this scene at once. It's non-permissive. I don't have to go put in situ thermometers in every building or power meters. I have high granularity in the coverage. I can see down to the level of the individual housing unit, and I have persistence. I can take one image every few seconds through the night, or in some cases, other sensors through the day. So we got interested in that and started to do some demonstrations using the view from our offices in downtown Brooklyn. This is a view of Lower Manhattan from our offices. There are about 1,000 buildings in the scene. The Empire State Building in the upper left is about 3.8 miles away. And we know the identity of every building in the scene, so we have access to all of the city records for these buildings. And so we started just by taking a image every 15 seconds through the course of many nights. This shows you what the image looks like. You can see the lights going on and off. Using an analysis inspired by astronomical techniques, you can analyze the on-off of every light in the scene. You can learn about energy use. You can learn about occupancy. You can learn about sleep-wake patterns. During the day, you can learn other interesting things. This shows you in the upper right a time lapse over about 1 minute during the day. You can see the traffic going by, not particularly interesting. But if you subtract the background, as we've done in the lower panel, you can see this cloud that emanates from one of the buildings, and we've colored it in red. What is that? Well, it's that. The use of heavy heating oil in New York City is the largest source of particulate pollution, more than the diesels. With this technology, one camera watching 1,000 buildings, we know who's doing it, where it's going, and needless to say, the environmental protection folks in the city are very interested in applying this in order to help alleviate this source of pollution. You can do other things to watch the city. An ordinary camera takes a picture in 3 colors, red, green, and blue. There are hyperspectral cameras that take pictures in 800 different colors at once. The spectrum associated with each pixel is characteristic of the lighting technologies used. In the lower left, I show you some representative spectra of fluorescence, high-pressure sodium, LEDs, etc. You take that scene of Manhattan, again with a single sensor, you can segregate the lights according to technology type, understand the penetration of advanced lighting technologies across the city, segregate it by demographic group, and then also investigate in real time the phenomenon of rebound. whereby if you buy a more efficient light, you're probably more tempted to use it more often, partially negating the efficiency gains that the better technology gives you. You can also look at the city in the long-wave infrared, the so-called thermal infrared. Here I show you 3 images of the west side of Manhattan in the thermal infrared, covering about 500 buildings. The upper right and then the middle were taken about 2 minutes apart. The difference image is shown on the bottom. You can see quite clearly some of the thermal plumes emanating from the buildings, but what caught our interest was that square on the lower right. As I said, we have information about every one of the buildings, and so we ID'd it, and it's that building which turns out to be near Google headquarters on 14th Street in Manhattan. And what's interesting is that row of cooling towers on the upper right. And evidently, we caught a cooling tower turning on. And so now I've got a way of watching in real time the HVAC operations of many hundreds of buildings at once, understanding energy use and understanding the contributions of those facilities to the urban heat island, which is an important aspect of city living during the summer. With a hyperspectral long-wave infrared instrument, you can do chemical ID of the plumes that you see coming out of the city. This shows some images again of the west side of Manhattan, and we see a tremendous amount of Freon 22 in a haze over the city. This is chlorodifluoromethane. It is an ozone eater. You may not buy this chemical in the US anymore. You may not construct facilities that use it for refrigerating anymore. But if you have legacy equipment or legacy stocks, then you can still use that, and evidently that's what's happening in New York City. Again, one would like to identify and encourage a switch away from this chemical. Okay, let me show you an example of how we can bring multiple data sources together in a tool that some of our researchers have developed for the citing of new developments in New York City. So if we could just click on that video, and we'll show it. It's about 3 minutes worth of video.
Why do two neighborhoods feel similar or different? Why does a new building change the character of a neighborhood and another doesn't? While the experience of a city is inherently subjective, the characteristics that shape the quality of it are not. To help answer these questions, we propose Urbane, a 3-dimensional multi-resolution framework that enables a data-driven approach for decision-making in the design of new urban developments. Through a data-driven understanding of the existing city and tools to evaluate potential new developments, architects, developers, and planners can both better collaborate and make more informed decisions. The creation of Urbane posed several challenges. First was integrating 2D and 3D urban data sets from different sources and that don't share a format. Second was the ability to perform 3D impact analysis such as landmark visibility and sky exposure in real time. Finally, creating a 3D interface that allows users to view and filter data sets and analysis at multiple scales. Urbane allows users to seamlessly explore the city based on multiple 2D and 3D data layers. For example, noise, where we can see a surprising density of noise complaints on 25th Street right next to a high school. And subway access, where the highest subway access density is in the financial district. The data can be explored at different resolutions, the city, neighborhood, and buildings. The opacity of the 3D buildings can be controlled for better visualization of data layers. Urbane uses a parallel coordinates chart that allows for easy and intuitive filtering of urban data sets. Here we filter neighborhoods for various attributes such as subway access and noise. The bold blue line represents the average of all Manhattan neighborhoods. The bold red line is the user-selected neighborhood, here the financial district. The parallel chart allows the user to vary a single element within a filtered scenario and see the range in neighborhoods that meet the changing criteria. As the noise threshold decreases, but jobs and subway are held constant, we can see the range of noisy to quiet neighborhoods that meet this criteria. Filtering of various attributes allows users to understand the characteristics of Manhattan neighborhoods. At the neighborhood scale, the same filtering system is applied to individual buildings. The blue line represents the average for the selected neighborhood. Here, we filter individual buildings for attributes such as built area, crime, and noise, identifying sites for potential development. Within that criteria, we vary crime from low to high, seeing a shift in sites from north to south. Once specific sites have been identified, Urbane gives users the ability to import geometry generated in other 3D modeling software and replace existing buildings, testing different tower sizes and designs over multiple sites. Here we see user-imported geometry color-coded by program. Residential is yellow, hotel is purple, and office is blue. Here is a range of mixed-use buildings being tested. Once buildings are imported, Urbane can compute the impact of imported buildings on sky exposure at the street level and the impact on the visibility of the existing context to selected buildings. This analysis can be used to evaluate the trade-offs between the value of the new development and its impact on the character of the neighborhood. This can facilitate the design and development process between architects, developers, and city planners.
Okay, let me close with some thoughts of lessons we've learned in 4 years now of developing urban informatics, working closely with the city and some parts of the private sector to apply big data techniques to urban problems. One is you really need disciplinary expertise. It's not enough to take a heap of data and throw a computer scientist or data scientist at it. You really need people involved who understand how the data was generated and how the analysis is to be applied. The second, at least in a city where there are many different kinds of data sources, heterogeneous data sources about the infrastructure, the environment, and the people, you really need data standards. You really need an ontology to understand how to hook these data sources together. For the work we're doing, data hoarding is a major problem. I've come to conclude that the second most basic human urge is to hoard data. The academics do it because it's priority in publishing papers. The commercial sector does it because of the economic value of the data, and government organizations do it because data is power and turf within a city government. For urban informatics, there's still a lot of confusion about who the customers are. City governments are perhaps the most obvious user, but they are not great customers. They're cash-strapped, and they tend to have really serious procurement rules. In the city, citizen acceptance is a big deal. Privacy is front and center in this business. Standards need to be established, protocols, best practices promulgated among the people who are doing this. And then finally, workforce. Data science is hot, but even hotter are people who understand both data science and a domain. In CUSP, my center, we have a one-year master's program. On Monday, we graduated 87 students with backgrounds that range from civil engineering to data science to cognitive psychology. We teach them about cities, we teach them about data, and needless to say, they all find jobs when they graduate with us. That's all I wanted to say. Thanks for your attention. I know we're about to go into a coffee break, and so I'm happy to take questions individually if you want to have a conversation.